So let's have a look at the course plan first before we dwell into carbon dioxide. What are we expected to do? This is the syllabus for this case at 4007, and this is the legal document between university and US students. There are theory and two parts of the course that one can take. Both the theory, which is essentially the exam, and then laboratory exercises. And I don't know what division, if it's how much credits there is to each one of these. But now let's see course content. Where is the here? I think we can. It's the second middle part here that relates to aqueous chemistry stuff. Chemical reactions of inorganic compounds in natural waters. This is easy to say and less easy to. Yeah, hello. No, that was just a noise. All muted. Fine. I mean, it's easy to say chemical reactions of inorganic compounds, which is a lifelong task to study more or less. But we will look at carbon dioxide and a few other stuff, metal ions, and look at the chemical equilibria that are present in natural waters. Sources of heavy metals. What is a heavy metal? You can look here, learning outcome. Let's see, toxicology. This is probably organic, yes. Then I think this is the learning outcomes for the inorganic part. Conditions of water system from variables pH and redox potential. This is very well describing the main content of the course. We will look at how stuff behave at different pH and how chemical compounds will affect the pH of solutions, and also the redox potential. This is slightly less known, I think, redox potential, because it's not it regards uptake or give away over the electron from some chemical compounds. This is less easy to grasp, I think. At least I think so. For the help of you, I've edited a couple of small documents. Fundamenta.pdf is the thermodynamics. It's only one page, so it's very short and condensed. And then the file here with the same name as the course is slightly less condensed. It deals a lot of with the acid bases, which you probably know quite well. Or unless you do, this is a possibility to what's it called, reiterate it and repeat it. So this is inorganic aqueous chemistry has sometimes been termed as general chemistry, but second level or something like that. If you want to read more, I downloaded the book from the library, and this is not the only book in environmental chemistry that is available at the library. But there are several, and they are freely available, so you can download them, many of them at least, in PDF format, if you become especially interested in some area. This is 300-400 pages or so, very heavily condensed information. But essentially every book with the title Environmental Chemistry or Aqueous Environmental Chemistry, they contain approximately the same material, or at least has a common part, has one part that is common to very many books. Well, this is the same with other chemistry books also. You can't find the general chemistry books that's not telling anything about Gibbs energy, for example. Lab is not containing anything yet, but there will be, we will have the 2 labs during the course, by the way. There have been some questions if we will both whether we will work from 9 to 5. I think that is what is written in the schedule, but perhaps we don't need to start at 9. My suggestion is but rather something like 10 o'clock or something like that, and probably we won't be working continuously until 5 o'clock in the afternoon either. But that doesn't mean that you should be sloppy and don't do anything at the lab. But try to do as much as possible, and I think it should be quite possible to do most of the different labs and then finish not very late anyway.
I'm sorry.
Yes.
Could you maybe tell us a bit more about the lab, because I don't really, like, maybe I missed some information, but I don't really know what it will be like. Is it on the computer or is it an actual, like, in-person lab? And what it will be about and so on, because I knew that it is on the schedule, but I don't really know what it is about.
The first one, for example, next week, the 13th, we go out and collect waters, natural water samples, and I suggest we go to some lakes close to university, so we don't have to travel a lot. This is allocated a whole day, but I guess that if we start at 10 o'clock or something like that, in order to avoid the worst crowding subway situation in the morning, then we will finish, say, 2 o'clock maybe, or if we even earlier. It's plenty of time allocated. And then the actual inorganic lab, it's analyzing these waters regarding some parameters in a course lab. So we will have 2 course labs at our disposal. We will look at alkalinity and some metal ions, some other ion content, sulfate ions, chloride ions, but this is regular wet labs, so to say. There should be no or hardly any risks associated with the labs compared to the organic part, for example, since it is mostly water samples, and I mean, depending on what you do, if you do alkalinity titration with hydrochloric acid, this is completely harmless from a toxicology point of view, at least. You shouldn't spill it on your metal watch or something like that, perhaps, but otherwise it's no risk.
That was actually, that was not why I was asking, it was just because I think the photolysis lab was originally intended to do in person, and then it was moved to a computer lab. So that was why I was asking. But
I see. No, we're not using any poisons, I would say, and any hazardous. Well, the most dangerous chemical we're using, which is of course extremely dangerous, is sodium hydroxide. But as long as you avoid getting it into your eyes or at the skin, the skin is no problem. You just rinse it off with the water. But it shouldn't be any toxicological risks associated with this. I don't know, depending on the situation, silver ions, they are not very healthy, of course. One should avoid to get them on the skin, but I mean, they are in water solution, so they don't, it's no risk actually dripping some silver ions in a solution. I mean, if you want to take extra care, avoid touching the solution or collaborate with some people. The worst one possible nuisance is the indoor conditions sometimes at Kjöl, where we will be. The air is very, very dry, but perhaps one can open windows and such. But I don't think it should be. This first lab is checking the samples from the lakes according to a few parameters. And then second lab is wastewater treatment. I'll see if we can arrange a study visit at some wastewater plant. And this is sometimes not extremely pleasant, depending on where one goes on this wastewater plant. But I'm not sure if they are actually open to in real life study visit, or if it will be an electronic study visit. Then we will also collect some normal seawater and analyze it for nutritions, for phosphate, essentially. Iodine is also used in this first lab. Iodine, aqueous solutions of iodine.
Thank you.
Yeah, you're welcome. More questions?
Yeah, so the Thursday the 14th and is it Wednesday the 20th? It's the whole day. It takes more time.
It's allocated the whole day at least.
Yeah.
Where from 10 up to 17 according to schedule, or even if you look here, labs till 18. But this is Hitesh who wrote, and this is not my fault. So I would say more reasonable 10 to 16, or a bit shorter.
Okay, yeah, thank you.
Yeah. And then we have a seminar here at 21st. That is in principle a follow-up on the labs, because you should write some report for the labs, and you don't have to write a long article with a lot of history and such things, but more or less report the results of the lab. But I think that a seminar that we I suppose this is stated as Zoom here. If you all have a possibility to show a few pictures, a few lines of written text or something like that, we can divide the different subjects that we have been looking at, the different parameters of this lake waters. We have 2 labs to discuss here. This is quite good to have a possibility to discuss with each other. That is a seminar. and the time here is just preparation for seminar. This could of course be done. You can start with it already next week, say Friday 15 individual studies, reading, calculating, or something like that, or preparing some results for seminars. And then I didn't include the last week, but there will be a part in the exam also of inorganic chemistry. So let's see, clock is 9:20. I suggest we run in. No, stop it. We run in 45 minutes approximately, and then have a 15 minutes break or something like that, and times free. And then afternoon will be allocated to calculation exercises. There are 4 different calculation exercises, and they connect very closely to what we have been speaking about during lectures. Do you all have computers available? I suppose so, but I mean, some people are looking at Zoom via mobile phones or tablets or something like that. Is it anyone without a computer? No, that's good, because that will simplify things a lot if you have access to a computer. What systems are you using? How many are you using? Windows, I suppose, most of you, or is this a correct guess from my side? Yeah, Natasha says thumb up. Anyone with a Macintosh? No, Arild raised hand, and 2 others. Let's hear. Or was it an indication that you're using Macintosh?
Yeah, I think we're a few with a Mac.
Yeah.
Yeah. Probably minority.
Ah, that's the usual thing. But then I'll try to prepare and see to that I have some help for both Windows people and Mac people. So no one is using Linux, I suppose, or am I wrong? That's not, no. Well, the content of the course, I mean, it's inorganic chemistry in water solution. This doesn't mean that we are completely uninterested in organic ions in water solutions, but or organic complexing agents for metal ions and such things. But it's not pure organic chemistry, at least. There could be carbon-hydrogen bonds in inorganic chemistry also. What we will look at is essentially acid bases, different compounds with respect to their acid base properties. And especially in aqueous solutions, we speak about hydrolysis and vitrification. Hydrolysis could be just reaction with the hydrogen oxide, that is water. Vitrification is perhaps a special word related mostly to minerals and such things when they react with water, and possibly with some other compounds dissolved in the water. And then we will also speak a lot about redox. Actually, we will connect these acid-base properties and redox properties in something we call Torbert diagram. And final thing is eutrophication, that is the process of lakes growing too much or something like that, because of that they have too much nutrition connected, and we will connect to fresh water and wastewater cleaning in the end of the course also. If you feel that you need to ask something, feel free to interrupt. Just raise a hand or just speak out. That is perhaps the easiest. Remember to unmute. The concept of acid rain is rather popular, or it has been more popular actually to speak about acid rain in the past than it is now, maybe. But everything that has some acidous character, for example, carbon dioxide, dissolves in water, and then the rain, the water droplets in the rain will become slightly acidous. Carbon dioxide is not a very strong acid, but depending on where you live on Earth, so it could also rain diluted solutions of hydrochloric or sulfuric acid or nitric acid or something. This is, of course, not healthy, but it's apart from that vegetation dies, so it's not an acute problem for humans or animals. Animals do not suffer very much from very dilute acid solutions, except as the vegetation dies and then we have nothing to eat. That is, of course, a side effect that is really bad. So usually the pH of rainwater is around 5.6, something like that, in this order. If you have pure water in contact with carbon dioxide in the atmosphere, normally the other stuff shouldn't be present in natural environments. This acid character of the rainwater, it could come by some wet deposition, or also dry particles that later react with something. I suppose you have noted, for example, some quotes that aluminum is an acidifier. How come that aluminum, that is a metal, could be considered as an acid or an acidifier? Well, I think it is mostly connected to the fact that aluminum ions can work as a transporter of acid ions or acidity. Aluminum ions are acid, so they can be said to transport the effect of acidity. This is a word map over some from some book in environmental chemistry, where one can look at where is this acid deposition especially high, and it's I'm not sure how accurate it is, but you can see over Europe, industrialized areas have a lot more acid deposition. Here is, what is this? This is China, something like that. Japan and the US. So this was an American book, so I suppose the US part of the map is more accurate. and I'm not sure how old it is either. Africa and South America and Siberia is no information, neither Australia, but I think one can connect acid deposition with inhabited areas of the world. Everywhere where there is, say, some combustion of wood or coal or oil, there will be a small addition of, say, sulfurous compounds to the atmosphere. And sulfur in contact with oxygen will produce sulfur dioxide and sulfur trioxide, which is equal to sulfuric acid. That is acidity. I think maybe sulfur is perhaps the most important element for heavy acidity, at least, or very severe acid rain. Carbon dioxide is less of a problem with respect to acids. Yeah, here is a map of Eastern USA, how it was worse back in the good old times. I think that is the take-home message from these maps. Here around some industrialized area, it's a lot of wet sulfate deposition, and in the modern, less past time, modern times, this is a notebook, and the acidity deposition has gone down. Probably gas cleaning from well, it's every burner that or all fumes that comes from burning of oil and coal, they are perhaps purified better nowadays than they used to be, hopefully, and perhaps also used less nowadays, because we're going towards more green, sustainable heating arrangements and such. But we will see if acid rain will disappear, not completely. How is acid rain taken care of? A simple way is to describe reactions with, for example, limestone, calcium carbonate, that is a major component of limestone. This is more or less equal to limestone. And when it finds some acid, here indicated just by a H+ aqueous, one can symbolically say that it dissolves this calcium carbonate. The carbonate is a basic ion, slightly basic at least, and it reacts very well. It's very eager to react with the hydrogen plus, so there will be a hydrogen carbonate ion formed. Hydrogen carbonate ion and calcium ions, they don't connect at all as strongly as calcium ions and carbonate ions. I don't know, do you see this as an ionic compound? Do you interpret this as calcium ions and carbonate ions? This is perhaps not obvious, but it's not a carbon ion and oxide ions. Then it would be better to see it as a covalent compound. But I think an easy description is this as an ionic, at least mostly ionic compound. This could also be demonstrated with other type of rocks. Silicates is maybe the most occurring type of rocks on Earth, silicates are much more stable than carbonates. So they react much less with H+, but they do react. What's in such places where there is well, silicates are the type of rocks that react less, then this acid rain may be a more serious problem. Well, it's simply because the hydrogen ions coming down from the sky, they don't react until after, say, 10,000 years. But if it's limestone in the ground, they react immediately. There is no acid rain problem on the island Gotland, for example, in the middle of the vad heter havet? Not North Sea, but the Baltic Sea. The large island Gotland contains a lot of calcium carbonate, so they have a vegetation that depends on the partly basic character of the ground and such things. Aluminum, acid rain can leach aluminum ions from soil, or what type of soil this is, if it's clay soil or if it's humus soils, doesn't really matter. There is a lot of aluminum available in the environment. I think several percent of the ground is composed of aluminum. And these aluminum ions, if they are dissolved in some way, they may be transported, and then they may replace hydrogen ions as a transporter of acidity. So one can say that the aluminum ion represents something acidus. It's a Lewis acid, according to the charge, but it's more difficult to see it as a Bronsted acid, maybe, but we can see if we can. Now let's see. Try to share a whiteboard here. Let's see if it works. Do you see one line over the screen here?
Yeah.
So aluminum, if it's a 3+ ion with waters around, then we can see it as some kind of complex like that. That may the aluminum 3+ is of course connected to the oxygen side of the water molecule, so it will attract the charge, sometimes represented by free electron pairs on the oxygen like that, heavily. So one can perhaps assume that it will attract at least one of the waters heavily, and we'll leave the others for the moment. So this is a hydroxide ion, and it has a negative charge, and it will compensate one of the plus charges, and the rest of the water molecule that was here will be released as a hydrogen ion. So this is a way to say that aluminum 3+ in aqueous environment is essentially working as an equivalent for hydrogen plus.
I don't think we see what you've written beside the aluminum water complex. Have you written something beside it?
Here?
No, Yeah, there too, we don't fully see what you've written, I think.
Now let's see. Good that you. Where is? You see it now?
We saw it, and yeah, now we see it. Now we see it.
Aluminum hexa aqua and aluminum with a hydroxide with a line below. You see that?
Yes.
Yeah.
Yeah, and a hydrogen ion to the most to the right.
Yes, exactly. What is written in brackets behind the hydrogen oxide, the hydrogen, sorry.
What is written where?
In brackets on the right next to the hydrogen.
Here?
Is that AQ?
That's AQ, yes.
Okay, thank you.
That's true. You will soon realize my bad handwritings. But protest. So
I was wondering, I was wondering a little bit, how exactly does the leaching work? Is that super complicated, or?
No, well, the leaching, how does it work? Yeah, it's now let's see.
Does it just mean react, or
It's a well, how does it work? We can take the calcium carbonate. This is a solid compound, and then when there is some hydrogens from outside that come and react, we don't give these detailed reactions, not with the arrows that the organic chemists do, for example, which is also a symbolic stuff. I don't think that nature knows the arrows, but if we say that a lot of hydrogen ions, if they sort of say that the surface of the material here is attacked by hydrogen ions, and something happens here, some acid corrosion, and then we will, as products on the other side, have these calcium ions and the hydrogen carbonate, that they don't form solids at all as easy as the calcium 2+ and the carbonate 2- ions do. But how does it work? Well, it must always be along some surface reactions at the surface. That is a reason why, for example, studying chemical reaction where they actually goes on, that is at the surface, would be an interesting subject, but it's quite difficult.
Mm.
You can, so to say, take a piece of a lump of calcium carbonate and a beaker with the acid and see that they do react. But in detail, I think there are some computer simulations that show up approximately, but it's just throwing balls of hydrogen ions towards here, and suddenly they do react, and then the contents here is not bound as strong as previous, and perhaps they are released in the solution. If they can come into solution, there may be a possibility for further attack. Yeah, this is perhaps it's not at all detailed.
All right, but the aluminum, it will basically be just a similar type of reaction, just with another starting compound other than the calcium.
Yes.
All right, and then the free aluminum ion would associate with water, and then it could
Exactly, produce some hydrogen ions, because I think the hydrogen ions, they are much more easily penetrating most solid structures. But there could also be, say, aluminum 3+ that come directly. This is a strong acid with large charge, positive charge here, and perhaps it will find some counterparts here. And either form a precipitate. There is aluminum metal, for example. It's a very reactive metal. It's not like sodium, but nearly. Chemically, it's like magnesium or something like that. It immediately reacts with water. So this is an impossible combination, or at least unless this is not balanced, but unless you want aluminum 3+ in water solution and hydrogen gas. This is the thermodynamic reaction that will spontaneously happen if you look up in tables and such. But you know that this is not the case. You can have a metal objects, some kitchenware, for example, made of aluminum. This is not at all a problem. Or you can have a water bottle of aluminum. And from a chemical point of view, this is very, very strange. Why doesn't it evolve hydrogen gas and disappears instantaneously? This is because aluminum immediately forms a layer of aluminum oxide around the aluminum metal, a thin layer, so that it's not visible. And this is extremely strong, so it will protect the aluminum from water. But from a long-term perspective, I think it will be water will be attacking through this. I mean, a long-term perspective is perhaps say thousands or millions of years or something. Digging down aluminum cans in the ground is a way to get rid of them, but they will stay a couple of years at least.
All right, yeah. I remember the aluminum oxide from the equilibrium course, but maybe
yeah.
Thank you.
And aluminum oxide is perhaps an excellent example of the acidity of aluminum, because aluminum ions are very acid and oxide ions are very basic. So strong acids and strong bases, they form stable compounds. Now it happens that aluminum oxide also fits to aluminum metal very well. So they are good neighbors, so to say. And thus it won't peel off easily of the metal object. Sorry, now
I have another question.
yes.
Sorry, and it might be a really, really stupid one, but I'm trying to connect this to a course that I previously had, which was soil sciences.
Yeah.
And there we talked about the concept of acidic cations and alkaline cations. And it was basically our professor told us that aluminum is considered an acidic cation, which now totally makes sense with this background.
Yeah.
But why are, for example, potassium or calcium considered alkaline cations? Or have you, like, do chemistry people use this concept as well? Or
Yeah, alkaline, I wouldn't say alkaline. Everything positive I would like to have as an acid. or as a not very if you can't I don't think one can sense the acid character of potassium or sodium. They are treated as non-acidic or also non-basic. But then magnesium, for example, slightly higher charge, so more acidus.
So it basically depends on whether how strongly the cation will attract the formerly negatively charged O of water and
Yes.
thus enforce a cleavage of the bond between O and H.
Yes, exactly.
Oh, okay. Thank you. That
And
makes sense.
if you take the hypothetical silicon 4+, this is way much more acid than anything we have available. So this will, together with OH2, if I write it like that, water, so it will immediately attack the water and release hydrogen ions. This is, I used to call it perverse acid, but it's directly related to the charge. It's not linear, so it's not so that mono positive ions are one acid character. Maybe pH in pure water is more or less 7. That is not affected. Here is perhaps 5 or something like that, slightly acidus. But with aluminum, it could be 1. So it's a lot larger step between magnesium and aluminum than between potassium and magnesium.
Okay, that makes sense. Thank you very much.
Yeah, and this is exactly the idea behind Lewis acids. This is the charge. How well is this ion attracting electrons from the electron pairs from the surroundings? This is not obvious, especially when it is a layer of water molecules around. With the aluminum 3+, then it's so large charge that it will attract the electrons from the water layer around it. So, yeah, but hey, we time runs. Clock is 9:52. Should we have a break? 7 minutes past 10. Is that okay?
Yes.
Sure.
I